Okay, let's continue detailing our model. What we have so far is a HEC-RAS model that has 8 cross sections, and those are getting data automatically from the terrain that we created. So that's good, and we can run it now. We can detail it a little bit. You can see there's lots of vegetation in the one that we're seeing here. If you see a top view, you can't even recognize there is a channel here. So of course, our goal is to detail it with this deck and then the culvert that links the channel to the pond, so we can learn more HEC-RAS. And of course, we can test different scenarios. What happens if we maintain this channel? Can we avoid flooding in parking lot here in a case of a heavy precipitation or not, and things like that. So to do that, we need to understand what was the condition when they built this, so we can compare it with the existing condition. And that's also helpful for detailing and adding things like the culvert and things like that. So basically, if you use a time machine in your Google Earth, just take the time back and do some measurements, you can easily recognize that this was a nice trapezoidal channel back then, and it had a bottom width 2.5 feet, top width of 19 feet, side slope horizontal to vertical 1.5, and a maximum depth of 5.5 feet. So we need to basically replicate that in our maintained condition. And as we do that, we can also make our existing model enable to have features like culverts. Right now, because it's all shows as surface of the earth, we can't really put a culvert in that. The way we do it is basically we model it. Right now, this light gray line is showing the situation in the model. We need to convert this actually to basically a trapezoidal channel, and some part of it is blocked with fixed sediment. Of course, when we delete this sediment, it's going to give us our maintained condition. In both situations I'm showing here, for maintain and existing with a filled sediment like this, you can add features like culvert and things like that. But in our current model, we can't do that. We can't put a culvert that is, just somewhere buried in the ground. So let's do that step by step. I'm going to my HEC-RAS window right here. So basically the HEC-RAS window, if I want to expand this a little bit, showing what I have done for making these changes. The way I do it is, personally, I choose this graphical editor. The graphical editor allows you to move things around easily, delete objects. If you want to delete this guy, just delete it, and things like that. So it's easy stuff. You can easily move objects. Like this is your bank station, right? You think this should be this number. So you can easily do these changes without typing digits in the window. So after you do this, going back, you want to make sure that the information I showed you is maintained in the model. So basically, what I'm showing here in this cross section, if I want to go up, down, showing it for different cross sections. Like this guy, let me show because it's nice and round. Okay, so what I've done for this one is basically, you can see only with these 4 points, I can create the shape of trapezoid as I was showing you in the first video. And of course, these are just station elevation. You want to make sure that when you get to this station, you go to the next one, you maintain the side slope. So let's show that. Of course, when you press the control button, your cursor changes to a ruler. So I'm showing that to make sure it's happening. Actually, I didn't do a very good job in picking the right point. So let me do it more carefully this time. This looks better. So I release it. Okay. So what I wanted to have is a side slope of horizontal to vertical 1.5. So HEC-RAS shows me the other way around. 0.67 is actually what I wanted. I wanted to have a bottom width of 2.5. That's happening, 2.5. I wanted to have a top width of 19. That's happening, length 19. And I wanted to have a maximum depth of 5.5 feet. So that's my maximum depth. And that's happening. So basically, this is, again, a manual process. You have a cross-section like this gray line. You edit points like this to enable a trapezoidal channel as is given to you in the as-built information. You can manually type it, or you can do it with a graphical method. At the end, you need to make sure that you're getting top width, bottom width, side slope, and maximum depth. So basically, this is how we get to this. Of course, next step for you gonna be tools. So you want to add fixed sediment elevations for your existing condition. So it's showing you what's that sediment. So let me pull up the cross section. I have this cross section 347, and it's showing me like this depth could be the sediment depth, which is basically the elevation. Let me make sure I'm reading it correctly. So this is 10, 11 right here. That's basically 11, more between 11.5 and 12. Or if I wanna show it like this in terms of depth, that can be, let me see, what's this distance? So it's about 3 feet depth of sediment I have here. So I go to my fixed sediment elevation, and for this cross section, for example, you can add 3, so that's 11.5. And then maybe you can do this same process and come up with different numbers. Maybe at this one I have 11.75. And 11.7 maybe here. Of course, you can update the plot so it shows you the sediment being formed. And then you can continue this process. So basically, you have existing condition. So just to save time for recording this video, I can show you what I've done here. Basically, the way you do stuff in HEC-RAS, you have a set of different things, right? So of course, you want to save your geometry as a new geometry and call it maintain, call the other one existing, so you don't, that's the best way to organize things. And once you have that, you can come up with a plan. So the nicest part about HEC-RAS is this plan. So basically, I have a series of different plans. This plan, you can see I have 3 types of geometry files. I have different files for the flow. So working with the plan, you can see how many plans I have here. So this is my maintain. Of course, I have saved this as an existing condition, and then each plan, as you can see, it's a combination of a geometry and a flow. So one of it is the high type condition, the other is a low type. So I'm opening for you the existing condition with high water situation, so which I have everything saved in it. Do you want to save existing geometry? So that's no, because I've already done it. You can ignore this warning. And then now it shows you what I have here for all the sediment and everything. You can see I have sediment. I've done this for all different cross sections, moving up and down. So that's something that that is done. So it's showing you basically the sediment window. If you do it, then I've replicated this sediment blockage in the channel. So I'm not working with something that is like just earth, and it doesn't allow me to model this deck and culvert. So that's done. And now I have a geometry saved for my existing condition. Then of course I have a geometry saved for my maintain condition. If I want to go back to that one, so definitely change things through the plan. Don't confuse yourself with changing and opening different geometry files. If you change your plan, then it automatically updates your geometry and flow data together. So going back to maintain condition, I wanted to show you another change I have done, and that's basically if I open the cross sections, you can see I'm now using numbers for the channel that is for the maintain condition, for the maintain concrete. So it's smooth concrete I have here. I didn't have it for I didn't have this low number for the existing condition. So two things need to change between maintain and existing. One is the roughness, the other is the actual geometry. So you want to show that now it's a nice and clean channel without any sediment and vegetation in it. Okay, so we have everything ready for us to add a road deck here and add a culvert underneath. So our river system is connected. Let's do that. First step is finding the closest cross section that you have. So we have 258. Our road deck is like 3-4 feet downstream of it. So first open this window, bridge culvert data, and add a bridge and or culvert. So once we add it, first step is having a road deck, and then we can add the culvert information just underneath the road deck. So let's do that. It's asking you a new river station for the river. Of course, we have 250 something close to it. So this can be our 250 for the river station, for the new bridge or culvert. So it automatically finds the upstream and downstream cross sections that you have adjacent to the 250 that you put here. You have 258 and things like that. So it's finding it for you, makes your job easy. So now that you have it, then you can go ahead and basically import your road deck information. So I showed you it's about 4 feet downstream of it. And the width, you can measure it on aerial imagery. It's just a 6 feet wide, tiny road. It's just a very, basically it's just a trail that passes. And then you can leave the rear coefficient and stuff like that. And what you can do here is basically now you at upstream and downstream, you need to identify some station elevation for the high chord. If you have a low chord, it's just a bridge. Or if it's more of like a blockage and there is a culvert underneath, so you can identify it here. Basically, you can start with elevation 0 all the way to the other side. So you can see 14 is my elevation, and then you want to continue this. So what if I put 0 here and high chord 14? You don't have a low chord here. You want to show it basically as a complete blockage. And then you can continue just on when you get closer here. Basically, you can put this as about this, like 46. You can put 11. And then, of course, once you apply it, it allows you to see what you have here. And on the other side, like 60 something, let's say 67, you want to put 11 maybe. And just to close it at the station very end 100, it's again 14. So let's show this to see if it makes sense or not. So it's creating something like this for you. Again, we're not exactly at this cross section. This red line is the one upstream. So basically, the way you do it is finding the elevation. You can double check it through your geometry. So basically, you have, once I do it, it shows something for me. I'm doing something here. This is the 4 feet. So let me zoom in and maximize the window a little bit. So the 4 feet, basically the 6 feet that I considering for, it's showing 6, considering for the deck width. And if I want to cut a cross section like this, it can show you what I have here. So that's the 11 that I have for the top of the deck. So this is the information coming from GIS data. I have 11, so it's more of a changing from upstream and a little bit down towards down and up. So what I have for 11 is basically this number, roughly this number for the road deck. So let's go back and continue our work here for deck. And for the downstream, you basically have about same numbers. Whatever you have actually is around 11, so you don't need this 14. So everything you put is basically 11 feet elevation for the deck. Of course, going to be same numbers for downstream. Just pick some points. I can put all the way from 0 to 100 with 11. So 0, 11, 100, 11. If you have lots of changes in the elevation of the deck, then you might need more points, but you're good for this. And basically, you can apply it. So then you can see this is forming right here too, 11. And then you can continue with other information. If you have a side slope, horizontal to this, horizontal distance to 1 step vertical for the embankment, like in this case, it's 2 for upstream, 2 for downstream. These are all coming from the geometry of the data. And then you can leave the rest, just if it's acting like a weir, if it's overtopping, then what coefficient you want to include, and then broadcasted, everything is fine. So you're basically done with information here. I'm showing you, we're considering an 11 for the deck in all cases. If you want to show more of the reality, the deck was something like this when I cut a cross section. So you can, of course, change this to 14 or something like that, but those are not visible because they're on the other side of this cross section. So this is good for the road deck. Okay, and then now do your culvert stuff. For the culvert stuff, now you want to basically show a hole in this. And then we know from the field, it's a circular 2 feet diameter culvert. That's what I have from my notes. And basically, now you need to show the distance to upstream and that. So distance to upstream XS, I have it as 4 feet in this case. Culvert length, that's something from the field information or as built. I have 12 feet long culvert, and then you need to consider some coefficient for the loss of the flow entering the culvert. Those can come from the literature. In this case, I have 0.7 for this, and asking what type of roughness you want to have for this. It's a concrete culvert, so then that's the condition when it's maintained, and basically some other information. Now you need to show it, right? You need to show where is this invert elevation located. So now I have only some information about the characteristics, not about the geometry. So if I want to show in upstream, is basically you need to basically have some elevation for upstream. This is about 8 and this is 9, so you can show it's between 8 and 9. What I have here is 8.3 for the invert of the culvert, 8.3. And downstream, then it's going to be somewhere here. And now I'm below 8, between 8 and 6. What I have in my notes, I have 7.6. 7.6. So if I okay it, then you can see, but we need to continue with barrel and everything. So let me do that. So it's asking what you have for barrel for the center line. And then I have, well, you need to call it like BR, whatever, upstream station and downstream station. So basically what station data you have for the barrel, just, you know, now that we identified the elevation part in this axis, now we need to show where in the x-axis is located. So you can see it's 50 here I have, and then it's between 50 and 60. So right, what I have here is basically, if this is 60, then that's 53. So I have 53 for the my exact note says I have 53.7, and for the downstream now I'm closer to 50 this time. So if this is 50, this is 55, then I'm 52.8. 52.8. Now you have enough information to show this. I can see the culverts showing, the road deck showing. So now basically you're done, and you want to exit this. You want to save geometry data, and basically now you have everything to run your model with a culvert. So let's do that. And basically I want to save this as a new plan, or I have already done that. So basically going to my run and then pick a plan that has this updated geometry. That's basically my, let's run it for the maintain condition. Okay, compute. And now you're done. Now you can generate results that have a culvert in it too. To generate those results, basically you're done with running the model. Just show profile, cross sections, tables, and things like that that I actually showed it in previous videos. This is my maintain condition for 2-year condition. So you can see water is backing up a little bit before the culvert. And of course, you can see this is subcritical easily. It's showing you the critical depth. So you have something above critical depth. So that means you have subcritical flow. Right at the entrance, it switches to the supercritical mode. So then it's like moving super fast. Now you are below the critical depth. And after the culvert, it's coming back to the subcritical condition again. So everything working as planned for the maintain condition. So now you can compare it. Is this the case for the existing or not with the culvert? For that, just basically change your plan. Open a plan. I ran this for maintained in the low water, so now I want to run it for existing in the low water. And then this warning, you can close. You can do basically compute here to make sure it's up-to-date results, then compare. Then you can see, because of many things happening, you have a bottom width, channel bottom increased because of the sediment. You have a higher number set for the roughness. Then you can see this is completely flooded even in the 2-year condition. And of course you can create and the results for the cross sections with sediment. You can see the actual channel is not flooded, so that's a good thing. That's actually for the 2 years. So if you compare this, maybe for your 10-year, you have everywhere flooded. And the situation showing you when you get to the culvert, it's overtopping the road deck. That's something bad. We don't want that happen typically, because it washes off the sediment and material from the road deck, and it closes the access, of course. So that's something you can have here. If you want to fancy it a little bit, of course, you can use your RAS Mapper window. This is a very robust tool for making fancy results. Basically, now you're showing the existing condition. For example, if you want to show the geometry we're showing. So let's not open too many things at the same time and make sure it makes sense. Right now you have geometry. You can add depth. So it's showing now for my 100-year, actually run that in parallel. I just didn't show the results in the previous window for cross section. So you can see I can actually get rid of the geometry right now. And also don't need to show too much of geometry, so it's not confusing. Now I can see for the 100-year condition, I have this entire area flooded. I can select this and then do particle tracing. So you can see how water is moving. It's now going to this culvert. And then from the culvert, you can see how fast they're releasing. So it's because it's supercritical and now coming back to subcritical. You can show velocities. We can change this, maybe just compare different scenarios if you want to do for existing. Just easily you can compare things. You can basically show also your geometry in it if you want to add your culvert. So you can see this is your road and this is your basically how velocities, for example, change. You can see very high velocities as you approach the culvert and as after you leave it. This is governing the flow for this part. If you select the actual variable, it shows you a scale, how your numbers. So when you have something about 8 feet per second, that's a very high velocity, but you have dark blue, which is about 2 feet per second for other areas. Lots of different ways. Now you can also you can show the depth. So it's scaled now with this bar. For the color tone, if I stop particle tracing, maybe I can now show velocities as vector. That's another feature. It's showing you numbers, and then you can move your cursor around. Right now I have about 4 feet of water in this condition. So these are your RAS Mapper tool. It allows you to generate 2D results based on 1D simulation. That's the nicest part of it. And for our future discussions, maybe we can also discuss a little bit about actually 2D modeling. So you don't do cross sections like this. You just use the actual terrain and then you create a mesh based of it. So you have a 2D model for actual calculations. The last thing I want to show about this RAS Mapper tool that we have for this video is to make actually nicest maps and figures for your client. So basically you can, right now I'm showing the terrain underneath. You can show the actual features on the ground. You have access to map layers. You can add a map layer, satellite imagery from ArcGIS, from Bing. Bing is the one that I use often. It's fastest for this platform. So you can turn this on and then of course turn this off, maybe make this a little bit transparent. So you can see what's happening underneath flooded areas. And again, you don't need to show them the computational cross section, so you can turn this off. but now maybe this is a nice map for them to see how this parking space is flooded under this event, and basically generate maps like this. Of course, you can compare different scenarios to each other. Like if you have for 10-year, maybe now it's your 10-year. So you can show 10-year event is basically producing a more manageable flooding in the parking space. So some part of it is flooded, some part is not. And then of course your depth and velocity both decreases. So different probabilities for flooding, different strategies for mitigation, everything can be nicely shown in this robust RAS Mapper tool. I hope you enjoyed this video.